question states that which of the following regular expression represents the language, the set of all binary strings having two consecutive zeros and two consecutive ones. So in the question, you are given only two conditions, that the language or the regular expression that you have to choose should have two consecutive zeros, that means 00, and two consecutive ones, that means a double one. You are neither specified in what order they must appear. In what order? That means you are not told whether the 00, the consecutive zeros, should come before 11 or vice versa, and neither you are told whether there needs to be some binary digit separating the two consecutive zeros and the two consecutive ones, or the both of them, the zeros and the ones, these double zeros and double ones, should be together. Okay, so basically neither order is specified, no order specified, and nor the placement of zeros and ones. Okay, no position of zeros and ones with respect to each other is specified. So basically you can have two types of strings. There has to be 00 in your string, then there may be some binary digits and then double ones, and there can be some binary digits before the zeros and some binary digits after the ones. Or the second kind of strings, binary strings, that you can generate with the given specified conditions is some binary digit followed by double ones, then some binary digits followed by double zeros, and some binary digits. Now these binary digits, these and these, any out of them can or cannot be zero, or you can say may or may not be zero. Any of these binary digits may be present or they may not be present. Okay, and same goes for these kind of strings. Okay, so these two types of strings cover all the cases of the binary strings or the language generated by these two conditions where 00 and 11 are present. So basically what kind of string, binary string or regular expression we have to specify? Anything that can be formed from 0 and 1, like any kind of string. By anything I mean 0 plus 1 star, that means any string that can be formed by 0 and 1 followed by a 0 0, then anything, I'm writing the short form, followed by a 1 1 and then anything. Alright, or representing this string, any string from 0 and 1 followed by 1 1, then any string. See here in this case 0 plus 1 star means lambda is also present, that means null string is also present, and again anything. Okay, so this expression can be represented by 0 plus 1 star followed by 00, again followed by 0 plus 1 star, 11 and 0 plus 1 star. Similarly, this corresponding expression is also 0 plus 1 star, 11, 0 plus 1 star, 00 and 0 plus 1 star. So if you take this part common, see in this expression, if you take 00, 0 plus 1 star, 1 1 and 1 1, 0 plus 1 star, 0 0, and take the first and the end part as common, you will end up writing this string. Okay, I'll write it down for you here. In both these expressions, the two common parts are the beginning and the end. Alright, so if you take these two expressions common, you will be left with this remaining part, and that will be forming your answer B. Alright, so this is the expression that will form the set of all binary strings that have 2 consecutive zeros and 2 consecutive ones. No other condition is specified, so you do not have to worry about any other condition. Okay, now coming to the second question, consider the following context-free grammar. In this grammar, you are given G1 and G2, and for each of these, you are specified the productions of them. Now you have to find out which of the following pairs of languages is generated by G1 and G2. Basically, you have to find out what language is generated by these two grammars respectively. So let's start with G1 first. If we start with the starting symbols S and use this production AS, that means the first production. So a string or the production would look like S goes to AS. Now, if I continue using this production AS and replace this S by AS again, my string would become like AAS and so on. As long as I replace this S with the production AS, I will get some number of A's followed by an S, and to terminate this string, I would have to use the second production, which is S goes to B. So at some point when I'm done generating all the A's, the starting A's of my string, I'll move on to the second production, which is S goes to B. And from here, I have two options. Either I can terminate this string by generating a single B, or I can continue generating B's by using the second production. So if I want to terminate by generating a single B, I'll use this first production, or I can continue to generate multiple B's by using the second production. Capital B goes to small b and B. Okay, so anytime, at any point, if you decide to choose any combination of these production, you'll basically end up generating some number of A's followed by one or more B. Okay. Now, why one or more B and not zero B? Because there is no case when you can terminate this string that is generated by A's without ending or coming to the production, the second production that is defined by capital B. Okay, and now you have to also consider that what does some number of A means. Is it one or more A, or is it zero or more A? Now in this case, some number of A's basically mean 0 or more A. Why 0 or more A? Because from G1 and the starting symbol of G1, you can directly jump to the second production using S goes to B. So in that case, you can skip all the A's and generate strings of the form B raised to power n, that is 1 or more B. Okay, so this is some number of A means 0 or more number of A's. Alright, so basically you as long as you repeat the production S goes to AS, you generate some number of A's. To terminate this string, that means to terminate the generation of A's, you have to make use of the second production B, and then the B production or the non-terminal B leads to a single terminal B or multiple B's. Okay. Or the second type of strings that you can generate using G1 is S directly going to non-terminal capital B. That means generating strings of the form single B or multiple B. So what is the language that we generate here? We basically generate A raised to power M, B raised to power M, such that M is greater than equal to 0 and n is greater than 0. Now you have to be very careful with this expression. Why? See, m has to be equal to 0 because I told you we can directly skip all the A's, and it has to be greater than 0 because we can generate A's. As well as at the same time, you have to tell that there is a possibility of generating one or more b's. So that is specified by n greater than 0. So some number of a's followed by one or more b. Now this is the language generated by G1. Now what is the language generated by G2? Okay, so in the exam you can find out what is the language generated by G1 and check in the option so as to eliminate certain options. So in this case, m greater than 0, no, we want m greater than equal to 0, m greater than 0, no, m greater than equal to 0. So we have eliminated these two options. Now comes m greater than equal to 0 or n greater than 0. No, we do not want an or condition. We want both these conditions to be satisfied. So this option is also eliminated and we are only left with option D. So you can mark option D straight away without even generating G2, because in this case the options are so listed down in such a way that you don't need to check for G2. But otherwise I'm also telling you for G2 how to check in cases when you are not so sure about the options. So for G2 we can start by using the production S goes to AA or S goes to BB. So this is very clear that in any case you have to start either with a A or with a B. There is no way in which you can generate a null here. Okay, so if you start with a A and you have to now replace this capital A or the non-terminal A, you have three options. You have options small a, capital B and epsilon or lambda string. So A, capital B and epsilon. If you generate A and capital A and terminate it with an epsilon, this would give you a single A, okay, or a single one A, single length string, okay, single A. If you replace this capital A with a B, you would end up having two other options which are BB or epsilon, and from B, if you choose epsilon, you would again terminate this string and a single A would be generated here also. But if you choose this string, you have generated one A, or you can you have generated some number of A's, and then when you replace it with a B, you have the opportunity of generating some more number of B's. These number of B's may or may not be equal to the number of A. So you have generated some A's and then you are generating some B. Okay, and see, you don't have to be confused that here I have written only one A, why I am writing here A raised to power M. You can always generate the grammar or the string by using the production S goes to AA, then replacing it with AA again, and then by after some number of A's you use the second production A goes to B to generate such kind of strings. Okay, so in this case you can always generate some number of A's by following this production, and if you have to terminate, you can use the lambda production, or if you have to follow these A's by some number of B's, you can use the second production A goes to B. Okay, so here what kind of strings we can generate? Some number of A's, or we can also generate some number of A's followed by some number of B's, an unequal or equal number of B's. And the second case, if I start my string with S goes to BB, what would be that case? I can replace it with either epsilon, that means I can end this string here only, or I can replace this B with another BB, that means I can generate some number of B. Okay, so what does the language generated by G look like? Basically, we are able to generate strings of this form such that M is greater than 0 or N is greater than 0. And why is it so? Because A raised to power M and followed by B raised to power N, at any point of time, both of them cannot be 0. If both of them, that means both m and n are 0, the string that would be generated would be an empty string, and this language does not accept an empty string, because as I told you, it will either start from a single a and terminate, the minimum length string that is possible is a single a or a single b. It does not accept lambda. So both m and n equal to 0 are not possible. Also, m equal to 0 is never possible, because m equal to 0 is possible only in the case we have only b's, and n equal to 0 is possible only in the case we have only a's. So this condition basically also translates to when m is 0, n cannot be 0, and when n is 0, m cannot be 0. Okay, so this is another way of writing which has been expressed in option D here. So this was, the second grammar was a little tricky, but yes, if you write down and try to find out all the cases, all the possible productions and the combinations that can be generated using these productions, then you'll be able to find out the actual language that is generated by these. So in such questions, it is easy, or it is preferred to find out one of the grammars or one of the language generated by a grammar, eliminate certain options, and then out of the remaining options you choose which would be the grammar generated by the second, which would be the language generated by the second grammar. First question is, which of the following languages is generated by the given grammar? And the grammar that you are given is S goes to AS, BA or BS or lambda or epsilon. Okay. Now clearly, if you have practiced generating languages from certain grammars, you'll know it that this is the language this is the grammar that generates this particular language, A comma B star. But let's observe all these options and find out why all these options are incorrect, and finally find out why the D option is correct. Okay, so starting with the first option, it states that this grammar generates a language in which there are some number of A's followed by an unequal or equal number of B's, and both of them can be 0 or they can be greater than 0. But this is clearly not a complete language that would be generated by this grammar, because this option excludes those strings that start with B. Okay, so A option is incorrect because the grammar would generate certain strings that would directly start with B using the production S goes to BS and would contain only B. Okay, so these strings are not included in the first option, the language generated or the language that is specified in the first option, and so option A is incorrect. So option A is incorrect because strings can start with B also. And these kind of strings are not specified by option A. Option B states that the language that would be generated would contain all the strings over A comma B such that W has equal number of A's and B's. But this is not correct. This is not completely correct. The language may generate strings that would contain equal number of A's and B's, but it would also generate some strings that have an unequal number of A's and B's. And how would that be possible? So if I write productions like S goes to AS, and again I replace this S with another AS, and then at the end I replace this S with BS, so AA, BS, and at the end replacing this s with a lambda or epsilon, I get AAB. So in this string, I have generated this string from this very grammar, and the number of a's and b's are not equal. So this language would contain other strings that are having a's and b's in unequal numbers. So this is also not the right option. Okay. Now coming to the third option, C option states that the language contains strings that have some number of a's and also the strings that have only some a's, only some b's, and only some a's followed by an equal number of b's. Again, this is not the case because the strings of the form b raised to power n, a raised to power n, or a raised to power m, b raised to power n, or b raised to power m, a raised to power n. That means equal number of b's followed by an equal number of a's. Okay, or b's followed by an equal number of a's, or some number of a followed by unequal number of b's. Here both the values are equal, n. Okay, you have to be very careful in reading the options. And here also some number of b's followed by an unequal number of a's. These are the strings that would be possible through this grammar. Okay, and at the end when we come to D option, we find out that what all strings can be generated using this grammar. an, bn, an, bn, or bn, an, or am, bn, or an, bm. Okay, so sorry, bn, and this is an. Okay, so basically all those strings that are possible and can be generated using the two alphabets A and B can be generated by this grammar, and the correct option is D. Okay, so this was not very difficult. If you have practiced enough number of grammars, you will be very easily do this question and grab marks. Now coming to the second question, it states that which of the following decision problems are undecidable. Now this is an important concept about decidability and undecidability. So let's see what are the options and statements given. The first statement is given NFA, N1 and N2 is the intersection of the languages generated by these NFA equal to phi. Is this statement or finding out the intersection of two languages is phi, is this decidable or undecidable? You have to tell that, and you have to also tell that given a CFG generated by this grammar and a string that belongs to sigma star, does X belong to the language generated by a grammar? So basically it is asking you that if you are given a string that belongs to the alphabet and a CFG for that, you have to tell whether a particular string is a member of that language or not. So is this a problem decidable or not? Okay. Now third is given CFG G1 and G2, is the language generated by G1 equal to the language generated by G2, and given a Turing machine M, the language generated by M is phi. So you have to tell which out of the four are decidable and which are undecidable. Basically you have to tell which are undecidable. Okay, so starting with the first statement, if we are provided with two NFAs, then we have to find the intersection of the languages that is generated by these NFA, we can easily find that using the cross product of the two NFA. So the important concept here that you have to remember or understand is cross product of two NFA or corresponding DFA. You can find the cross product for a DFA also and for a NFA also. So if you are given two NFA and you find the cross product, and if there is a state in that cross product, the resulting NFA or the resulting finite automata that is formed, if it has a single state that forms the final state of both the NFA N1 and N2, then the intersection will be non-empty, and if the single state. There is no single state that forms the final state of NFA, N1 and N2. Then the intersection would be phi. So I would write it here. So first thing you have to do is find the cross product of two NFA, and after that you have to see if there is any state in the resultant finite automata. In the resulting finite automata which acts as the final state for both N1, for both N1 and N2. Okay, so if yes, this is true, there is a state that is final state for the languages generated by N1 and N2, then the intersection is not null. Okay, if it is false, there is no common state, then yes, the intersection of the two languages is empty, or there are no common strings in the language generated by these two NFA. Okay, now coming to the second statement, given a CFG and a string, does X belong to the grammar that is generated by the CFG? So basically it asks you about the membership problem, whether it is decidable or not. Okay, so this problem, since we could decide it using a particular set of steps, finding the cross product and then finding out if there exists a particular state to decide if the intersection is empty or not. So this problem is decidable. Okay, it can be decided, or the result can be achieved. A yes and no answer can be achieved using a sequence of steps that can be followed. Okay, now coming to the second statement, it basically asks you if the membership of a string in a particular language, this problem is decidable or not. Yes, membership of a CFG, membership of a string in a CFG is a decidable problem. G is again decidable, and it can be decided using CYK algorithm. Okay, so again this is a decidable problem. Coming to the third statement, given CFG, G1 and G2, is the language generated by G1 and G2 is equal? Is it decidable or not? No, this is not decidable, or you can say it is undecidable. So this is an undecidable problem. Equality of two languages generated by the CFG is an undecidable problem. The last statement is, given a Turing machine M, is the language generated by the Turing machine equal to phi? That means the emptiness problem of a Turing machine or the language generated by the Turing machine is again undecidable. So all those statements that are undecidable, all the decision problems that are undecidable are third and fourth. So C is the correct option, 3 and 4. So in this question you have to remember that equality problem, emptiness problem are certain cases in which you cannot really decide by carrying out an algorithm or certain sequence of steps whether what would be the correct answer as true or false or yes or no. Okay, but there are other cases like finding the intersection of two languages generated by two NFA, whether it is phi or not, and the second case, membership algorithm, in which we can find out very easily that whether it is a decidable or undecidable problem. So that's all for today's lecture. I hope all the concepts from this lecture are clear. Please mention in the comment section below how did you find the video. If you understood the questions, please like it and share it with your friends. Subscribe to our channel of Easy Engineering Classes and hit the bell icon to get the notifications of our latest upcoming videos. Thank you for watching. Stay tuned. Good luck.